Right now, high above your head, a river of wind faster than a jet plane just buckled. For weeks it held the sky calm and quiet. Then it snapped into a giant curve, and everything changed. That one bend is loading the eastern United States with 10 days of danger. We are going to ride that wind together. You will feel the air turn into a furnace that never cools, even at midnight. You will watch walls of water swallow whole highways in minutes. You will stand under a storm wider than 5 states, and you will meet a spinning giant being born over warm ocean water. One wave in the sky decides all of it, who stays safe and who gets caught. If this grabs you, tap like and subscribe so the next danger never catches you off guard. Now take a slow breath. We begin. For almost 3 weeks, the sky over the eastern United States did close to nothing. Morning after morning, the same soft haze, the same warm, sticky air that barely moved. People stopped checking the forecast because the forecast stopped changing. Boring, safe, forgettable. High above all of it, though, something was waiting. 7 miles over your head runs a fast band of wind that steers almost every storm in the country. For those quiet weeks, it sat far to the north, stretched out flat and straight, like a long, empty highway with no exits and no turns. When that wind runs straight, weather slides by fast. A shower here, a breeze there, nothing sticks, nothing builds. Forecasters have watched this exact setup for a long time, and they know a secret about it. A calm, straight pattern is a spring being wound tight. The longer it holds, the more energy it stores. Heat piles up over the land. Moisture piles up over the ocean. The whole system leans closer and closer to a tipping point, and from the ground you would never feel it coming. Then the computer models blinked. Every day, powerful machines take millions of measurements from balloons, planes and satellites, and they run the future of the sky forward in time. For days, those machines had shown more of the same. Flat, quiet. Then, almost all at once, they showed the straight wind starting to bend. A small dip here, a small bulge there, tiny at first, like a single ripple crossing a still pond. The scientists knew what a ripple like that can grow into. A bend in that high wind does not stay small. It feeds on the difference between cold air to the north and warm air to the south, and it swells. A little curve becomes a giant curve, and a giant curve can lock the weather in place for days, trapping heat under one part of the country and dumping storms on another. That is the danger hiding inside the calm. The quiet was the deep breath before the plunge. Picture a garden hose lying loose across a driveway. Turn the water up slowly, and the hose begins to whip. The faster the water, the wider the swings. The wind 7 miles up behaves the same way, only the swings are hundreds of miles across, and instead of water they move heat, rain and storms. By the middle of that 3rd quiet week, the models all agreed on one thing. The straight wind was about to buckle, and when it did, the eastern half of the country would sit right in the crosshairs. The calm had an expiration date now. You could count it in days. Most people went on with their lives, mowing lawns, planning cookouts, thinking the biggest problem of the week was the humidity. They had no idea that a single change far above the clouds was about to reach down and touch every one of them. A change so distant it may as well have happened on another planet, yet close enough to decide how the next 10 days would feel for 100 million people. To understand what happened next, you have to meet the wind itself. It has a name, it circles the whole planet, and it holds more power over your day than almost anything else in the sky. Its next move was already beginning. The wind that runs the whole show has a name. It is called the jet stream. Start with the size of it. The jet stream is a river of air that wraps all the way around the Earth, thousands of miles long, flowing from west to east. It flows on without end, circling the planet for as long as the planet has had air. Now the speed. Down where you stand, a strong gust might reach 40 miles per hour and knock over a trash can. Up in the jet stream, the wind often blows faster than 100 miles per hour, and in its strongest streaks it can top 200. That is quicker than a race car screaming down a straightaway, happening silently every second, 7 miles above the roof of your house. Pilots learn to use it. A plane flying east with the jet stream at its back can arrive early, pushed along by that free river of speed. A plane flying west into it fights a headwind the whole way and burns extra fuel. The same wind that shortens your flight home is the wind that steers the storms toward your town. Here is the part that matters most for the next 10 days. The jet stream forms along a border. the line where cold air from the north meets warm air from the south. Cold and warm air shove against each other, and that shoving, spun by the turning of the earth, creates the fast river of wind in between. Where the temperature difference is sharp, the jet stream is strong. Where it fades, the wind slows and begins to wander. That wandering is everything. When the jet stream stays tight and straight, it acts like a fence, keeping the cold up north and the heat down south, moving weather along like cars on a fast freeway. When it loosens, it starts to swing north and south in huge loops, and those loops decide who bakes and who floods. Think of it as the conveyor belt of the sky. Storms are the packages. The belt decides where every package gets dropped. Speed up the belt and everything rushes past. Kink the belt and packages pile up in one spot until they spill. For weeks the belt had been running straight and fast over the East Coast, carrying trouble away before it could grow. That was the calm you felt. But a border in the sky is always restless. The heat building over the land was sharpening the difference between the hot south and the cooler north, and a sharper difference means a wilder wind. The jet stream was getting ready to move, and once a river that big starts to swing, nothing on the ground can stop it. Scientists can now watch this happen almost live, tracking the wind with satellites that stare down from far above. They saw the first wobble form over the middle of the country. They measured it. They ran it forward, and every model told the same story. The straight fence was about to bend into a giant loop, and that loop was aiming for the east. One curve in this river can change the lives of 100 million people. The next chapter is the moment it finally broke. It started over the Great Plains as a single gentle curve. For days the jet stream had run flat across the country. Then, near the middle of the map, it dipped south just a little, the way a rope sags when you stop pulling it tight. A small thing? If you'd been standing under it, you would have felt nothing at all. Yet that small dip was the first domino, and the rest were already lined up behind it. Once a curve like that forms, it grows on its own. The dip pulls cold air farther south on its western side. On its eastern side, it lifts warm air farther north. That swap makes the temperature difference even sharper, and a sharper difference feeds the wind, and the stronger wind carves the curve deeper still. Round and round it goes, each step making the next one bigger. Within 2 days, the gentle dip had become a deep valley in the wind, and right beside it, over the eastern United States, the jet stream bulged far to the north into a giant dome shape. That northern bulge is the key to everything that follows. Where the jet stream arcs north like that, it leaves a huge zone of high pressure sitting underneath it. Air there begins to sink and settle. Skies clear. The sun pours straight down with nothing to block it. Day after day, that spot gets hotter and drier because the bulge is stubborn and slow to move. Meanwhile, the deep valley to the west fills with the opposite. Rising air, clouds, rain, storms. So one buckle in a single wind sets up 2 disasters at the same time, side by side. A furnace under the bulge, a storm factory in the valley, and the spinning border between them becomes a battle line where the wildest weather of all will explode. Picture a bedsheet held tight and flat by 2 people. That is the calm jet stream. Now have one person lift their corner high and the other drop theirs low. The sheet folds into a big S shape. That S is exactly what the sky did over North America, except the folds were each the size of several states, and instead of cloth, they were made of moving air 100 times heavier than it looks. The scientists watching their screens knew this was locked in. An amplified curve this large can sit nearly still for a week or more, and a sky that stops moving is a sky that piles up trouble. They also knew the timing was cruel. The bulge parked itself right over the most crowded strip of land in the country, the chain of cities running down the coast where tens of millions of people live shoulder to shoulder. The forecast maps filled with colours that make meteorologists lean forward in their chairs. Deep reds for heat, bright greens and purples for heavy rain. All of it clicking into place because of one bend 7 miles up that most people would never see. The straight wind was gone. The giant loop had arrived, and it was settling in to stay. Loops like this have a name. Scientists have studied them for almost 100 years, and their strangest power is the way they can freeze in place. pinning one kind of weather over the same towns for days on end. That power is what turns a hot afternoon into a deadly week. The giant loops in the jet stream have a name. Scientists call them Rossby waves. They're named after Carl Rossby, a scientist who, almost 90 years ago, worked out the math behind why the high wind swings north and south instead of running straight. His idea was so powerful that we still use it every single day to predict the weather, tested and proven millions of times over. Here is the simple version. The Earth spins. Because it spins, moving air travels in curves instead of straight lines. Push a river of wind toward the pole, and the spin bends it back toward the equator. Push it toward the equator, and the spin bends it back toward the pole. The result is a wave that rolls around the whole planet, swinging up and down over and over, like the humps of a giant sea serpent circling the globe. Each hump north is a ridge, each dip south is a trough. Under a ridge, air sinks and the weather turns hot and dry. Under a trough, air rises and the weather turns wet and stormy. Those two shapes, riding around the world, control who sweats and who shivers on any given day. Now for the frightening part. Most of the time these waves slide slowly eastward, so no single town stays under a ridge or a trough for long. The heat comes, then leaves. The storms come, then leave. Life goes on. But sometimes the waves grow very tall and very slow. When a wave stretches far to the north and far to the south, it drags its feet. It can nearly stop, parking a ridge over one region and a trough over another for a week or longer. Scientists call this a stuck, or blocked pattern, and it sits behind many of the worst weather disasters in history. When that happens, whatever weather the sky's holding gets time to build into something extreme. That is exactly what clicked into place over North America. The wave over the country had grown tall enough to stall. The ridge over the east coast was going to sit still, holding its dome of sinking, heating air over the same cities day after day. The trough to the west was going to sit still too, firing storms into the same regions again and again. Think of it like a traffic jam in the sky. Normally the weather flows past like cars on an open road. A blocked pattern is a stalled truck across all the lanes. Everything behind it piles up, and only when the truck finally moves does anything get through. Scientists have also noticed something troubling in recent years. As the far north warms faster than the rest of the planet, the temperature difference that drives the jet stream is shrinking, and a weaker jet stream may wander into these tall, stuck waves more easily. Researchers are still testing this idea, and it remains an open debate, yet many worry these blocking patterns could be growing more common. For the people under this particular block, the debate hardly mattered. What mattered was simple. The lid had closed over their sky, and it was about to trap a heat unlike anything they had felt in years. Under that stuck ridge, the air was already beginning to bake. Under the stuck ridge, the air began to sink, and sinking air is hot air. Here is why. When air drops from high up toward the ground, the weight of the atmosphere squeezes it. Squeeze any gas and it heats up, the same way a bicycle pump gets warm when you push air into a tyre. Now imagine that squeezing happening across half a dozen states at once, every hour, for days. The whole lower sky warms up and refuses to cool. That is a heat dome. Scientists use the name for a reason. A strong ridge of high pressure acts like an invisible dome clamped over a region. It presses down. It pushes clouds away. It leaves the sky a hard, cloudless blue, so the sun blasts the ground from dawn to dusk with nothing to soften it. Each day the land soaks up more heat than it can shed by night, so each day starts a little hotter than the last. Picture a lid on a pot of soup. Leave the lid off and steam escapes, keeping things from boiling over. Clamp the lid on and the heat has nowhere to go. The soup climbs toward a boil. A heat dome is that lid. Only the pot is an entire coastline, and the soup is the air you breathe. The numbers climb fast under a dome like this. In a normal summer week, a coastal city might top out in the middle 80s. Under a strong heat dome, that same city can push past 100 degrees for several days in a row, and the air can feel even hotter than the thermometer says. During recent East Coast heat domes, the air has felt like 110 degrees once humidity is counted in. That is hot enough to send hundreds of people to the emergency room in a single afternoon. And the dome does more than cook the air. It traps whatever is already floating in the sky. Smoke, dust, and pollution get stuck under the lid along with the heat, so the air grows hazy and hard to breathe. In recent summers, wildfire smoke drifting down from Canada has pooled under these domes, turning the sun a strange orange and pushing city air quality to some of the worst on the planet. People with asthma feel it first, gasping on days that look, from indoors, deceptively bright. The dome is stubborn. That is the cruel part. A passing hot day is easy to survive. You sweat, you drink water, you wait for the cool of night. A heat dome takes the night away. The ground stays so warm that darkness brings little relief, and the next morning the baking simply resumes, a little worse than before. Day 2 is harder than day 1. Day 3 is harder than day 2. The danger stacks. Forecasters could see this dome holding firm for the better part of a week, right over the crowded coast. They began sounding the alarm early, urging people to find cool air and check on their neighbours, because they knew what history teaches. Heat is the quiet killer. In a normal year in the United States, it takes more lives than hurricanes, tornadoes, and floods combined. Most of those deaths share one thing. They happen after dark, during the hours when the body expects a break and the heat dome refuses to give one. To understand why, we have to leave the wide sky and go down into the streets of a city, where the concrete itself has become a weapon. Walk out onto a city street at night in the middle of a heat dome, and the ground breathes heat back at you. You can feel it through your shoes. The sidewalk, the road, the brick walls, all of it soaked up sunshine all day long, and now, hours after sunset, all of it is slowly letting that heat back out. The city has become a giant radiator, warming the very air you were hoping would cool down. Scientists call this the urban heat island, and it is one of the meanest tricks in all of weather. Here is the cause. Country ground, covered in grass, trees and soil, handles heat gently. Plants sweat out water and cool the air around them, the way sweat cools your skin. Dark city surfaces work the other way. Asphalt and concrete drink in sunlight and store it like a battery, then release it for hours after dark. Add millions of cars, air conditioners, and buildings all pumping out their own warmth, and a city cooks itself from the inside. The difference is bigger than most people guess. On a hot night, the heart of a big city can run 10 to 15 degrees hotter than the green countryside just a few miles away. Same region, same sky. One neighbourhood cools off and gets a decent night of sleep. Another, wrapped in concrete, stays dangerously warm until sunrise. That gap of 10 or more degrees can be the difference between discomfort and a trip to the hospital. Picture a parking lot on a summer afternoon. You know how the air shimmers above the blacktop, how you can feel the heat rising in waves before you even touch the ground. Now imagine a whole city built out of that same blacktop, holding that same shimmer long into the night. That is what tens of millions of people were about to try to sleep in. It gets worse the higher you go and the poorer the block. The hottest apartments are often the ones without air conditioning, in older buildings, in crowded neighbourhoods with few trees and little shade. Studies across American cities have found the same sad pattern again and again. The parts of town with the least money and the fewest trees tend to run the hottest, sometimes far hotter than wealthier areas only a short drive away. The heat dome plays favourites. It hunts the places least able to fight back, and the heat island does something sneaky to the whole region. By keeping the nights warm, it feeds the dome. A city that never cools down helps hold the heat in place, so the next day starts hotter, which warms the next night more, which starts the next day hotter still. Round and round, the temperature ratchets up. For most of the year, the urban heat island is a mild nuisance. A few extra degrees, barely worth a thought. During a stuck heat dome, it turns into a matter of survival. The same streets you walk every day, the same buildings you pass without a glance, quietly become the most dangerous place in the whole region to spend a summer night. Which raises the real question at the heart of a heatwave. Why is the night so deadly? Why do more people die in the dark than under the blazing noon sun? The answer lives inside your own body, and it is stranger than you think. Your body has one main way to cool itself down, and the heat dome is about to break it. That tool is sweat. When you get too hot, tiny glands push water onto your skin. As that water dries into the air, it carries heat away with it, leaving you cooler. It is a beautiful, simple system, and it works so well that we barely notice it running all day long. But sweat has a weakness, and a warm night finds it. During a normal summer, the temperature drops after sunset. Your body uses those cooler hours to catch up, to shed the heat it built during the day, to rest and reset before the next round. Sleep itself depends on it. Your core temperature naturally dips at night, and cooler air helps that happen. A cool night is the pit stop that keeps the engine from overheating. A heat dome cancels the pit stop. When the night stays hot, above 80 degrees, hour after hour, your body never gets to unload the day's heat. It keeps working, keeps sweating, keeps straining with no break. Your heart beats faster to move blood to the skin. You lose water and salt you cannot easily replace while asleep, and slowly, quietly, your core temperature creeps upward through the night instead of falling. That creeping is what kills. If the body's core climbs too high and stays there, the sweating system finally fails. The skin goes dry. The internal heat has nowhere to go. This is heat stroke, and it can damage the brain, the heart, and the kidneys in a matter of hours. The frightening part is how gentle it looks from the outside. A person may simply seem tired, confused, or sleepy, then drift into something far worse while everyone assumes they are only resting. Now the numbers make brutal sense. Doctors have long known that most heat deaths strike overnight and in the days that follow, as the strain piles up with no chance to recover. That is why forecasters watch the overnight low temperature so closely. A day that hits 100 degrees is survivable if the night falls into the 60s. The same hot day becomes a killer when the night refuses to drop below 80. Picture a phone battery you can never fully charge. Each night you plug it in, but the charger barely works, so each morning it starts with less power than the day before. Run that pattern long enough and the phone dies. Your body under a heat dome faces the same slow drain, night after night, with the charger broken. This is why a heat wave is so sneaky. It kills in silence. The danger arrives in the dark, in the hours when people feel safest, tucked in their own beds. By the time a warm night has done its damage, the sky outside looks perfectly calm. Forecasters kept hammering the same message as the dome settled in. Find cool air. Check on the old and the sick. A quiet person may already be in trouble, because inside this heat, the human body has a hard limit, an exact line where cooling stops working entirely. Scientists have measured it, and under the wrong mix of heat and moisture, that line is closer than almost anyone realizes. Scientists have found the exact temperature where the human body can no longer cool itself, and it is lower than you would ever guess. To understand it, you need to know that the number on a thermometer only tells half the story. The other half is humidity, the amount of water already floating in the air, and humidity decides whether your sweat can save you. Remember how sweating works. Water leaves your skin, dries into the air, and carries your heat away. That drying is the whole trick. Now here is the problem. Air can only hold so much water. When the air is already packed with moisture, your sweat has nowhere to go. It sits on your skin in useless beads, dripping, doing nothing. You're soaked, you're miserable, and your body keeps heating up with no way to stop. Scientists measure this danger with something called the wet bulb temperature. The idea is clever. They wrap a thermometer in a wet cloth and let the water evaporate, exactly the way sweat evaporates off you. If the air is dry, the water dries fast, the thermometer cools way down, and the wet bulb reading falls far below the real temperature. If the air is thick with moisture, the water barely dries, the thermometer stays high, and the wet bulb reading climbs close to the real temperature. In short, the wet bulb number tells you how much help your sweat can actually give you, and it has a hard ceiling. For years, scientists believed that once the wet bulb temperature reached 95 degrees, a healthy human could no longer survive, even resting in the shade with all the water in the world to drink. At that point, the air is so hot and so wet that sweat stops working completely. Your body has no way left to shed heat, and your core temperature climbs until your organs fail. Recent studies suggest the true limit may sit even lower, closer to the upper 80s on the wet bulb scale for many people, especially the old and the sick. Here is the part that should make you sit up. A wet bulb of 95 degrees can arrive at air temperatures that sound almost ordinary. It can happen around 105 degrees with very high humidity, the kind of steamy, soupy air the East Coast knows well in the deep of summer. The most dangerous corner of a heat dome is often the muggy, sweat-soaked coastline, where the ocean feeds the air with moisture and the dome traps it all in place. Imagine stepping out of a hot shower into a small bathroom with the door closed and the fan off. That thick, wet, breathless air, where you start sweating instantly and never seem to dry, is a small taste of a high wet bulb day. Now stretch that feeling across an entire region, for days, with no cool room to escape to. For most of the coast, the wet bulb stayed below that deadly line during this event. Uncomfortable, dangerous, and still survivable with care. Yet in the muggiest pockets, on the worst afternoons, it crept close enough to frighten the scientists watching the data. The heat, it turned out, was only the first weapon in the sky, because the same dome that bakes the land picks its victims with a cruel kind of order. The heat hunts some people long before it touches the rest. A young, healthy adult can take a lot from a heat dome. Their heart is strong, their body cools well, they sweat freely, bounce back overnight even when the night runs warm, and shrug off a rough day. For them, a heat wave is mostly a sweaty, sleepless annoyance. For others, the same air is a slow-moving threat, and three groups stand right in its path. First, the old. As people age, their bodies grow slower to sense heat and slower to cool down. Their sweat glands work less well. Many take medicines for the heart or blood pressure that quietly make it even harder to shed warmth. An elderly person can be dangerously overheated and barely feel it, sitting quietly, unaware anything is wrong. That is why so many heat victims are found alone, in homes without air conditioning, having never called for help. Second, the very young. A baby's body is tiny, and it heats up far faster than an adult's. Infants cannot tell you they are too hot. They cannot get themselves a drink or move to a cooler room. They depend completely on the grown-ups around them to notice. Every summer brings the same heartbreaking headline, "A child left too long in a hot car," where the temperature can climb by 20 degrees in 10 minutes and turn a parked vehicle into an oven. Third, anyone whose body is already fighting something. People with heart disease, lung disease, or kidney trouble start the day with less to give. Add the strain of extreme heat, and a body already working overtime can be pushed past its limit. Outdoor workers face their own version of the danger, spending whole shifts in the blaze because the job demands it, on rooftops, farms, and construction sites where the heat has nowhere to hide. There is a fourth group, and it cuts across all the others. The people with no way to cool off. Air conditioning turns a deadly heat dome into a survivable one. A single cool room can save a life, but cooling costs money, both to own and to run, and when a heat wave sends everyone reaching for the same power at once, some cannot afford to keep it going. Others have no unit at all. During past heat disasters in American cities, investigators found the same grim thread running through case after case. The victims were most often old, alone, poor, and cut off from a working source of cool air. Picture a marathon where most runners get water stations along the way, while a few are told to run the same distance with none. They start on the same street, they face the same heat, yet their odds could not be more different. A heat dome runs that unfair race across a whole city at once. This is why forecasters and doctors beg people to do one simple thing during a heat wave. Check on your neighbours. Knock on the door of the elderly man down the hall. Call the aunt who lives alone. A 2-minute visit can catch the early signs of trouble long before they turn deadly, at the exact moment when a glass of water and a cool room still make all the difference. But even the people with air conditioning were about to face a new problem, one that could take their cool air away in an instant and hand the heat dome its deadliest opening yet. The power grid was starting to strain. The one thing standing between millions of people and the full force of the heat dome was electricity, and electricity was about to become the weakest link. Think about what a whole region does at the same moment during a heat wave. Everyone turns on the air conditioning. Every home, every store, every office, every hospital, all pulling power at once, hour after hour, refusing to let up because the heat refuses to let up. The demand for electricity rockets to the highest level of the entire year. The power grid was built to handle a lot, but a stuck heat dome pushes it toward the edge in 2 ways at once. The first is that soaring demand. More air conditioners running means more electricity flowing through the wires and machines that carry it. The second is sneakier. The heat itself weakens the grid. Power lines sag and lose efficiency when they get hot. The big transformers that manage the flow run hotter and struggle to cool down, especially at night when they normally get a break. The same break the heat dome has stolen from everyone. So at the exact moment the grid is asked to do the most, the heat leaves it able to do less. Push hard enough, and something gives. Sometimes the power companies act first, on purpose. To keep the whole system from crashing, they lower the voltage, causing a brownout, where the lights dim and machines run weak. Or they cut power to one neighbourhood at a time, a rolling blackout sharing the pain so the entire grid stays standing. Other times the choice is made for them. A transformer overheats and fails, a line goes down, and the lights simply go out with no warning at all. In recent heat waves, hundreds of thousands of homes have lost power at the worst possible time during the hottest, most dangerous days. One event across the eastern states left more than 900,000 customers in the dark, while the heat index still sat above 100 degrees. Now the danger multiplies. A blackout in mild weather is an inconvenience. You light a candle, you wait, the food in the fridge holds for a while. A blackout in the middle of a heat dome is something else entirely. The one tool keeping people alive, that cool room, vanishes in a second. An apartment without power in this heat can climb past 90 degrees indoors within hours, turning a place of safety into a trap. The people most at risk, the old and the sick, are often the least able to just get up and leave. Picture a crowded stadium on a blazing day where the water suddenly shuts off. For a while everyone is fine, then slowly the crowd begins to suffer, and the ones already weakest go down first. A grid failure during a heat dome does that to a whole city, quietly, house by house. This is the hidden chain reaction inside a heat wave. The heat drives up the demand. The demand and the heat together strain the grid. The strained grid fails, and the failure removes the very thing protecting people from the heat that started it all. Each link makes the next one worse. Forecasters and power companies watched their systems groan under the load, hoping the wires would hold until the dome finally cracked. And crack it would. But the way it cracked was going to trade one disaster for another, because the same heat feeding this dome was quietly building the fuel for something violent along its edge. All that heat piling up under the dome was quietly loading a weapon along the dome's outer edge. Here is the setup. In the middle of the heat dome, the sky stays clear and calm because the sinking air there crushes clouds before they can grow. That is why the worst heat comes with bright, cloudless days. But a dome has a rim, a border where the sinking hot air meets cooler, more restless air pushing in from outside. And that rim is where the trouble brews. Meteorologists have a nickname for it. They call it the Ring of Fire. The name fits. Around the northern and western edge of a strong heat dome, thunderstorms line up and march along the border like sparks around a hot stove. The hot dome acts almost like a mountain of warm air, and storms are forced to ride up and over its edge, firing off one after another. While the centre of the dome bakes in dead calm, its rim can erupt with some of the most violent weather of the whole summer. Why does the edge turn so wild? Two ingredients meet there in just the right way. The first is heat and moisture, the fuel. All that hot, wet air the dome has been building is packed with energy, like a room slowly filling with gas. The second is a trigger, a push of cooler air or a ripple in the jet stream sliding along the rim. Bring a spark to a gas-filled room, and the whole thing explodes in an instant. The edge of the dome is where the spark finally reaches the fuel, and remember the giant loop in the jet stream. The deep trough carved out to the west on the far side of the ridge was steering cool disturbances straight toward the dome's northern rim, one after another. Each one was a fresh match struck near all that stored energy. Picture a campfire that has burned down to a huge bed of glowing coals radiating heat. The centre is too hot to touch, still and quiet. But toss a handful of dry grass onto the edge, where the coals meet the cool night air, and flames leap up at once. The heat dome is that bed of coals. The passing disturbances are the handfuls of grass. The rim is where everything catches. This is why a heat wave so often ends in a storm. The very heat that tortures a region for days becomes the fuel that blows it apart. The longer and hotter the dome, the more energy it stacks up, and the more explosive the storms along its edge can become when the pattern finally breaks. For the crowded coast, this meant the misery was about to change shape. The people praying for the heat to end were going to get their wish, and then some. The cool relief would arrive riding inside walls of wind and rain strong enough to flatten trees and flood streets. Along that rim, The afternoon could still touch the middle 90s even as the first storm clouds boiled up, the heat and the violence sharing the same sky. Forecasters could already see the first line of storms taking aim, forming along the rim where the dome's heat surrendered to cooler air moving in. The dome had spent days loading the weapon. Now something was about to pull the trigger, and the first blast would come as a wall of wind you could hear coming from miles away. The most violent storms of this whole event were born from the hottest hours of the day. It sounds backward at first. You might expect a blazing afternoon to bring only more heat. Instead, that heat is exactly what powers the storms that follow, because heat is fuel, and the sky spends all day loading up. Here is how it builds. As the sun climbs, it bakes the ground, and the ground warms the air just above it. Hot air is light air, so it wants to rise, the way a hot air balloon lifts off. All afternoon, the sun pumps more and more of this warm, buoyant air upward, and the atmosphere grows unstable, like a pot of water inching toward a boil. Weather scientists even have a way to measure how much explosive energy is stacking up, and on the worst days, that energy climbs to some of the highest readings of the year. For hours, a cap of warmer air up above can hold the lid down, keeping the storms from firing. The energy just keeps building underneath, waiting. Then, late in the day, something breaks the cap. A ripple in the jet stream, a push of cooler air, the edge of the heat dome, and all that stored energy lets go at once. The result is a storm that towers into the sky. Warm air rockets upward, sometimes climbing more than 8 miles high, punching into the freezing upper air where it builds an anvil-shaped cloud you can see from 100 miles away. Inside, water is lifted, frozen and slammed together, throwing off lightning and unloading rain. The more heat the day stored, the taller and angrier the storm grows. Now comes the part that catches people off guard. These storms often hit hardest at night. During a heat dome pattern, the biggest storm clusters frequently fire in the evening and roll on through the dark hours, feeding on the warm, juicy air the day left behind. So the same night that should bring relief instead brings a different terror, a line of storms crashing through while a city sleeps. People wake to their windows rattling, their power flickering, and a roar outside they cannot yet see. Picture shaking a bottle of soda all afternoon over and over, the pressure building inside with every shake. Nothing happens while the cap stays on. Then someone cracks it open in the evening, and everything that was quietly stored explodes out in seconds. The daytime sun is the shaking. The evening trigger is the twist of the cap. This is the cruel trade at the heart of the pattern. The heat that made the days unbearable becomes the fuel that makes the nights dangerous. The pattern flows straight from one hazard into the next. The furnace simply reloads itself as a storm, and the storms taking shape along the rim of the dome were becoming something rare. Fed by days of stored heat and steered by a stalled jet stream, they began to organize, lining up shoulder to shoulder into a single connected front. A scattered thunderstorm is loud and brief. What was forming now was far larger and far meaner, a formation with a name that makes storm chasers go quiet. The line was coming together. It began as a single dark line on the western horizon, low and long, stretching farther than the eye could follow. This was the first organized line of storms, born along the boundary where the heat dome's furnace met the cooler air pressing in. Weather forecasters had watched it come together on radar for hours, a string of separate thunderstorms slowly linking arms until they formed one continuous wall marching east. A boundary in weather is simply a border between two different kinds of air, warm and cool, wet and dry. Air pushing one way, meeting air pushing another. When storms find a boundary like this, they love to line up along it, because the boundary itself gives them a place to grow, feeding warm air up into each storm along the seam. As the line matured, it began to build its own engine, and that engine is the key to why these lines turn so dangerous. Every thunderstorm has an updraft, warm air rushing up, and a downdraft, cooler air and rain crashing down. In a well-organized line, all those downdrafts pool together at the ground into a mass of cold, dense air called a cold pool. That cold pool spreads out along the earth like water poured across a table, and its leading edge shoves under the warm air ahead of the storm, lifting it, firing up fresh storms right at the front. The line becomes self-feeding. It builds the very conditions it needs to keep charging forward. You can often see this leading edge coming. A dark, low shelf of cloud rolls out ahead of the rain, curved and menacing, stretching across the whole sky from one side to the other. Wind picks up fast. The temperature drops 10 or 15 degrees in a matter of minutes as the cold pool arrives. Dust and leaves swirl up. Then the wall hits. Picture a snowplow pushing a growing pile of snow down a street. The plow is the cold pool. The pile in front is the warm air being shoved upward. As long as the plow keeps moving, the pile keeps building, and the storms keep firing along the front edge. A well-organised storm line ploughs across the land exactly like that, only the pile it pushes is made of thunderstorms. For the towns in its path, the line brought a sudden, roaring assault. Blinding rain, lightning striking every few seconds, and wind, straight-line wind, slamming forward at highway speeds. In the strongest parts of the line, gusts can top 60, 70, even 80 miles per hour, strong enough to snap branches, peel off roof shingles, and send anything loose flying. This first line was a serious storm on its own. Trees came down. Power lines fell across dark roads. Yet forecasters studying the radar felt a deeper worry, because this line carried every ingredient it needed to grow into something worse. A single storm line is bad enough. But when a line like this keeps its engine running for hundreds of miles, refusing to weaken, feeding on heat the whole way, it earns a special and feared name. That was exactly the path this storm was on, and the name waiting at the end of it means damage on a scale few storms ever reach. When a storm line races for hundreds of miles without dying, it becomes one of the most feared storms in America. It has a name, a derecho. The word comes from Spanish, and it means straight ahead. It was chosen more than 100 years ago to describe storms whose winds blow in one powerful straight line, roaring forward like a battering ram rather than twisting like a tornado. And that straight-ahead motion is exactly what makes a derecho so terrifying and so vast. To officially earn the name, a storm has to do something extreme. Its wind damage must stretch for at least 250 miles in a nearly unbroken path, with gusts of at least 58 miles per hour along the way, and stronger blasts scattered throughout. In plain terms, a single storm has to punch a damage trail longer than the distance from New York City to Washington and beyond, all in one shot, often in just a handful of hours. The biggest derechos go far past that. Some carve paths of 800 miles or more from the Midwest all the way to the coast in a single afternoon and evening. Imagine one storm doing damage across a stretch as wide as a third of the whole country, moving so fast it can cross several states before the sun goes down. How does one storm grow so monstrous? It comes back to that cold pool and the endless supply of heat. A derecho is a storm line whose engine has locked into overdrive. Its cold pool at the ground is deep and powerful, surging forward and firing new storms so efficiently that the whole system races ahead at 50 or 60 miles per hour, as fast as a car on the highway. And in a heat dome pattern, there is fuel everywhere. All that stored heat and moisture along the dome's rim feeds the beast mile after mile, so instead of weakening, it can actually grow stronger as it charges east. The winds inside are the real danger. A strong derecho can unleash gusts of 100 miles per hour matching a serious hurricane, except this arrives with almost no warning and covers a much wider path in a single day. The bow-shaped line of storms bends forward in the middle, where the wind punches hardest, showing up on radar as a giant archer's bow drawn across the map. Picture a bulldozer the size of several states, driving across the land at highway speed, its blade made of pure wind. Everything in its path takes the hit at once, across a front hundreds of miles wide. That is the scale of a derecho. For the people in this storm's path, the sky would have gone from hot and hazy to black and screaming in minutes, a roar like a freight train. Trees bending, then snapping. Whole forests can be flattened in the same direction, thousands of trees pushed down like matchsticks, a signature that tells scientists later exactly where the worst wind struck. The first reports came fast. Power out for hundreds of thousands, roads blocked by fallen trees, roofs torn open, and the line kept charging east toward the coast, still fed by the heat it was leaving behind. The wide, roaring winds of the derecho were only one way this storm could strike. Hidden inside it was a smaller, sharper kind of blast, one that can slam a single neighborhood in seconds and is so often mistaken for a tornado. Hidden inside these storms is a burst of wind so sudden and so violent that people who survive it often swear a tornado came through. It was straight-line wind, and it works in a completely different way. A tornado spins, twisting air into a narrow, whirling column. A straight-line wind blows out and forward, all in one direction, driven down from the storm and then rushing across the ground. And while a tornado carves a narrow path, straight-line winds can hammer a wide area all at once. The most dangerous version has a name. Weather scientists call it a downburst. Here is what happens. High inside a thunderstorm, a huge mass of rain-cooled air suddenly plunges toward the earth, like water dumped from a giant bucket. When it slams into the ground, it has nowhere to go but out, spreading in every direction at tremendous speed. A strong downburst can produce winds over 100 miles per hour, as fierce as a major tornado, punching straight down and then blasting outward across everything below. The smallest and sneakiest kind is called a microburst, packed into an area less than 2.5 miles wide. It hits fast, lasts only minutes, and vanishes. For years, microbursts were a deadly mystery to aviation, because a plane taking off or landing could fly straight into one and be shoved toward the ground by a sudden, invisible wall of air. After several tragic crashes, scientists studied them intensely and built special radar to spot them, and air travel became far safer as a result. That is hard-won, proven science. Now think about the total damage. A tornado is more violent at its very centre, with the strongest ones spinning faster than any straight-line wind. But tornadoes are usually narrow, often only a few hundred yards across, and they touch a small slice of ground. Straight-line winds spread wide. Across an entire summer, these winds knock down more trees, snap more power lines, and cause more total damage in many regions than tornadoes do simply because they strike such large areas so often. The drama of a tornado grabs the headlines. The broad grinding damage of straight-line wind quietly adds up to more. Picture the difference between a drill and a sledgehammer. A tornado is the drill, boring a fierce, narrow hole. A downburst is the sledgehammer, smashing a wide, flat blow across everything in reach. Both do terrible harm. The sledgehammer just covers far more ground with each swing. For the towns under this storm, the straight-line winds arrived as a single shocking blast. One moment the air was still and heavy. The next, a wall of wind flattened everything loose, bent the trees to the ground, and was gone almost before people understood what hit them. Trampolines flew over fences, big trees toppled onto cars, roofs lost their shingles in a heartbeat. In the space of a single minute, a calm street turned into a scene of splintered wood and downed wires. The storm was showing its full strength now, a giant line of wind and rain grinding across the eastern states. Yet the more scientists studied systems like this one, the more they realized something almost unbelievable about them. A storm this big does more than pass through the weather. It begins to create its own. A storm this large does something that sounds impossible. It begins to build its own weather system, separate from the sky that created it. Scientists call a giant, organized cluster of thunderstorms like this a mesoscale convective system. The words simply mean a middle-sized system built from many storms working together. One thunderstorm is a single engine. This is dozens of engines fused into one machine, often growing large enough to cover an area the size of an entire state. And once it reaches that size, it stops merely reacting to the weather around it. It starts making its own. Remember the cold pool, that mass of chilled air spreading out beneath the storms. In a system this big, the cold pool becomes a force of its own, a pocket of dense, cool air pressing on the land, steering where new storms form and where the winds blow. The system builds its own miniature front, its own boundaries, its own wind patterns. It carries a little weather world along with it as it travels. Some of these systems create something even stranger, a slow, wide spin at their heart. As the cluster grows and the winds curve around it, a broad rotation can develop in the middle of the system, a swirl tens of miles across. Scientists call it a mesoscale convective vortex. It turns gently compared to a tornado, yet it can be remarkably stubborn. This spin can survive long after the storms fade, drifting along through the next day as a quiet swirl in the sky. And then, when fresh heat and moisture arrive, it can spin up a whole new batch of storms from its leftover energy. The system gets reborn from its own ghost. Picture a huge whirlpool forming in a river. Even after you stop stirring the water, the whirlpool keeps turning on its own for a while, pulling everything nearby into its spin. A mesoscale convective vortex is that whirlpool, written across the sky, wide enough to swallow a city and slow enough to last for a day or more. This is why these storm systems can be so hard to predict. They rewrite the forecast as they go, laying down their own boundaries that decide where tomorrow's storms will strike. Forecasters watching one of these giants know the map they drew this morning may need to change by afternoon because the storm itself is now shaping the weather. The largest of these systems can rain and rumble for a full day or more, travelling across several states before finally weakening. Along the way, they can drop enormous amounts of water, spin off pockets of damaging wind, and leave a trail of knocked-out power and flooded roads hundreds of miles long. For the eastern states, this meant the danger was settling in to stay. A storm system this organised was in no hurry to leave. It had built its own engine, its own spin, its own weather, and it could keep the hazards coming long after a normal storm would have blown itself out. But the deepest danger from a system like this was still building, and it came from the rain, from the way this storm was about to dump it in the same places over and over again. The flooding was about to begin. The most dangerous thing a storm can do is stop moving, and this one was about to do exactly that over the same unlucky towns. Weather forecasters have a chilling word for it. They call it training. Picture a railroad track with train car after train car rolling over the same spot, one behind the other, all following the same path. Now replace the train cars with thunderstorms, storm after storm, each one sliding over the same neighbourhoods, dropping its rain on ground that is already soaked, then handing off to the next storm right behind it. That is training, and it is how the worst flash floods are born. Here is why it happens. Sometimes the winds that steer storms line up in a way that sends every new storm along the identical track, like beads sliding down the same string. A stalled jet stream, exactly the kind in this pattern, is a perfect setup for it. The storms keep forming in one spot, riding the same path, and pouring their water onto the same small area for hours. The rain totals from training storms can be staggering. A single strong thunderstorm might drop an inch of rain and move on, and the land shrugs it off. But when storms train over the same place, that spot can receive 3, 5, even 8 inches of rain in just a few hours. That is a month's worth of rain, or more, falling on one town in an afternoon. The ground cannot drink it fast enough. The water has to go somewhere, and where it goes is where the danger begins. Think of pouring water onto a dry sponge. At first the sponge soaks it up, but keep pouring and the sponge fills, and soon the water just runs off the sides and floods the counter. The land beneath the training storm is that sponge. Once it is full, every new inch of rain becomes runoff, rushing downhill, gathering into streets and creeks and low spots, rising fast. And this rain was falling on ground already primed for disaster. Earlier storms in the pattern had soaked the region. The soil was full, the rivers were high. So when the training set in, the water ran off almost as fast as it fell, with no room left to absorb it. For the people below, this was the moment the storm turned from a wind threat into a water threat. Roads that were dry at dinner became rivers by dark. Small creeks that a child could hop across swelled into churning torrents. Basements filled. Cars stalled in water that looked shallow and turned out to be deep. All of it from rain that fell on the same spot again and again because the storms lined up on a track and refused to leave. Forecasters flooded the airwaves with warnings, urging people to move to higher ground, to stay out of flooded roads, to take the water seriously. They knew what was coming because they had seen this exact setup turn deadly before. A few inches of water sounds harmless. Most people believe they can walk through it or drive through it without much risk. That belief is one of the most dangerous mistakes a person can make in a flood, and understanding why it is so wrong could save your life. The water was rising, and it was far stronger than it looked. 6 inches of moving water can knock a grown adult off their feet, and almost no one believes it until the moment it happens. That number sounds impossible. 6 inches barely covers your shoes. You have splashed through deeper puddles without a thought. So how can water that shallow drop a full-grown person? The secret is in the word moving. Still water, like a pool or a bath, just sits there. You can wade through it easily because it stays put. But moving water is a different animal. It carries weight and speed together, and water is far heavier than it looks. A single cubic foot of it weighs more than 60 pounds, about as much as a large dog. Now picture that weight rushing past you, foot after foot after foot, every second, all shoving in the same direction. Even a shallow, fast flow can hit you with the force of a linebacker at a full sprint. And here is the cruel math. The force of moving water grows explosively as it speeds up. Double the speed of the water and its push becomes about 4 times stronger. So a flow that felt harmless at a slow crawl turns into a battering ram when it picks up pace, even if the depth barely changes. The deeper it gets, the worse the odds. At about 1 foot, moving water can float many small cars, lifting the tyres just enough to break their grip on the road. At 2 feet, that same rushing water can carry away most vehicles, even big trucks and heavy sport utility vehicles that feel unstoppable in a parking lot. Once a car starts to float, the driver has lost. The water decides where it goes now, and it often goes somewhere deadly. Think about standing waist deep in the ocean when a strong wave rushes past your legs. You feel that hard tug, that pull that nearly sweeps your feet out from under you, and that is just one wave. A flood is that same force, only it never stops pulling. It keeps coming, minute after minute, hour after hour, dragging at everything in its path. There is one more trap hidden in moving floodwater, and it may be the worst of all. You cannot see through it. Floodwater is thick with mud, so it hides what lies beneath. A road that looks like it has a few inches of water on top might have washed away completely underneath, leaving a hole deep enough to swallow a car. That gentle brown sheet across the pavement can hide a drop into churning water over your head. This is why every flood warning carries the same simple plea. Never walk or drive into water when you cannot see the ground beneath it. What looks like a shallow, easy crossing can be a killer in disguise, and the people who die in floods are very often the ones who thought the water looked harmless. The storms in this pattern were dumping rain faster than the land could handle it, and all that water was on the move, sliding downhill, gathering, and rising. In the worst spots, it was about to do something that gives flash floods their name, turning a calm, dry gully into a roaring river in the time it takes to eat lunch. The flood was about to arrive without warning. A flash flood can turn a dry creek bed into a raging river in the time it takes to eat lunch. The word flash says it all. Regular river floods build slowly over days, giving people time to pack up and move. A flash flood strikes fast, sometimes within minutes, often with almost no warning, and that speed is exactly what makes it so deadly. Here is how it forms. When those training storms dump inches of rain on a hillside or a city in a short time, the ground cannot soak it up fast enough, so the water runs off downhill following the land. Every low spot, every ditch, every creek and storm drain becomes a channel, gathering water from a huge area and funneling it all toward the same narrow paths. Rain that fell across many square miles suddenly squeezes into one small creek at once, and that creek explodes. A stream that was ankle-deep and gentle in the morning can rise 10 feet or more in minutes, roaring where it once trickled. By the time someone standing nearby notices their shoes are wet, the water can already be at their knees, and a minute later at their chest, rising faster than a person can climb to safety. The most frightening part is that a flash flood can strike a place where it is not even raining. Picture a canyon with a dry, rocky floor, a popular spot for hikers under a clear blue sky. Miles upstream, out of sight, a storm unloads. The water races down the canyon and arrives as a wall, a churning brown surge of water, mud, rocks, and broken trees, crashing through without warning. People have been swept away on sunny afternoons, never knowing a storm was raining far above them. Think of a bathtub with the drain wide open. Turn the faucet on gently, and the water slips down the drain, and the tub stays empty. Now blast the faucet on full, faster than the drain can handle, and the tub fills in seconds. The land in a flash flood works the same way. The drains, the creeks, the rivers, they can only carry so much. Overwhelm them, and the water has nowhere to go but up and out, spilling across everything nearby. And the water does not come clean and clear, it comes armed. A flash flood picks up everything in its path: logs, fence posts, trash cans, boulders, even cars. All of it turns into battering rams riding the current, smashing into bridges, buildings, and anyone caught in the flow. The water alone is dangerous enough. The debris it carries makes it far worse, and it is why rescuers warn you to never trust the surface of floodwater, because you cannot see the tree trunk tumbling toward you underneath. In this pattern, the flash floods came in waves. A storm would train over a town, the creeks would leap their banks, roads would vanish under brown water, and just as it began to drain away, another storm would roll over the same spot and start it all over again. The ground stayed soaked. The rivers stayed high. Each new burst of rain had less room to go than the last. For most people, the danger arrived in one specific place. A place they felt completely safe. A place they used every single day without a second thought. It arrived on the road, inside their cars. More people lose their lives in floods inside their cars than in any other place, and it happens for reasons that feel almost unfair. Study after study finds the same grim fact. More than half of all flood deaths in the United States involve a vehicle. Someone comes to a flooded road, decides it looks shallow enough and drives in. Seconds later, they are in trouble they cannot escape. Why do so many careful, sensible people make this deadly choice? Start with how hard it is to judge floodwater from behind the wheel. From the driver's seat, a flooded road can look like a simple puddle, especially at night when your headlights only skim the surface. You cannot see how deep it is. You cannot see whether the road underneath is still there or has washed away into a pit. The water looks calm and shallow, so the crossing feels safe. That single misjudgment is often the last one a person makes. Now add what water does to a car. A car feels heavy and solid, 2 tons of steel, unstoppable, but water cares nothing for that. At around 1 to 2 feet of water, a car begins to float because the air sealed inside makes it buoyant, like a giant metal boat. Once it floats, the tyres lift off the road and lose their grip, and the driver loses all control. The car becomes a raft with no paddle, spun and shoved wherever the current wants, often sideways into deeper, faster water. Then the water does something worse. It pushes. Remember how moving water hits with enormous force. Just 1 to 2 feet of rushing water can shove a floating car right off the road and sweep it downstream into a swollen creek or a drainage ditch where the water is deep and violent. The engine floods and dies, the electric windows may quit, and the pressure of the water outside can make the doors nearly impossible to open. Picture trying to push open a door with a large person leaning against the other side. That is what floodwater does to a car door, only the person never gets tired. Escaping becomes a desperate fight in the dark, in cold water, often with the car filling fast. This is why the Weather Service repeats one short phrase again and again during a flood. Turn around, do not drown. 6 words, built to save your life. It means the moment you see water across a road, you turn your car around and find another way, every single time, no matter how shallow it looks and no matter how late you are. A flooded road is one of the few dangers where doing nothing, simply refusing to drive forward, is the choice that keeps you alive. The people who survive floods are very often the ones who turned back at the water's edge and felt a little silly doing it. The flooding was spreading now, creeping from the creeks and roads into the places where people live and travel in huge numbers. The water was finding its way into the heart of the cities, into the tunnels and stairwells and low corners where a crowd of people can be trapped all at once. The most dangerous place of all was underground. A city can turn a heavy rain into a trap, funneling water straight into the exact places people cannot escape. Out in the countryside, floodwater has room to spread out and soak in. A city gives it nowhere to go. Roads, sidewalks, roofs and parking lots are sealed hard surfaces that shed water instead of drinking it. So when the rain pours down, nearly all of it runs off at once, racing across the pavement toward the lowest ground it can find. And a city is full of low ground built by human hands. Think of the whole city as a giant bowl with the pavement as its sides. Every drop that lands slides toward the bottom, and the bottom is where people gather. The drains try to keep up. Beneath the streets runs a hidden network of pipes and sewers, built to carry rain away. But those pipes were designed for ordinary storms. When a training storm dumps a month of rain in an afternoon, the drains overflow in minutes, and the water backs up, bubbling out of grates and gutters, rising in the streets with nowhere left to drain. Then it finds the openings that lead down: subway stairs, parking garages, underpasses beneath bridges, basement apartments. All of these sit below street level, and floodwater pours into them like water, finding the drain in a sink. In recent storms, video has shown water cascading down subway stairways in sheets, turning stations into underground rivers and stranding trains. Drivers have been trapped in underpasses that filled faster than they could back out, the water rising over their windows in moments. A stalled car in a flooding underpass is one of the most dangerous places a person can be, because the same dip that catches the rain also catches the driver. The deadliest trap of all is the basement apartment. In big, crowded cities, millions of people live in apartments partly or fully below ground because they cost less. During one recent storm across the northeastern states, a sudden burst of extreme rain sent water flooding into these basement homes so fast that people could not get out in time. The water blocked the only stairway, pressed the door shut, and rose toward the ceiling. Many of the victims of that storm drowned in their own homes, in neighborhoods far from any river, killed by rain alone. Picture standing at the bottom of a stairwell as water pours down the steps toward you, faster and faster, filling the space from the floor up. The one way out is the way the water is coming in. That is the terror of an underground flood, and it can unfold in a matter of minutes. This is the hidden danger of flooding in a modern city. The very things that make city life work, the pavement, the tunnels, the underground homes, become weaknesses when the water rises. A storm that would barely trouble open farmland can turn deadly the instant it hits a dense grid of concrete and low doorways. Emergency crews raced through the streets, pulling people from cars and basements as the water climbed. The rain kept feeding it, and overhead, the same storms doing all this had one more weapon left, spinning quietly inside the marching line. A threat that would drop from the clouds with almost no warning at all. Something was starting to rotate. Buried inside that long line of storms, something began to spin, and a spinning storm means a tornado may be about to form. Earlier, the storms attacked with straight-line wind, blasting forward in one direction. A tornado is a different beast entirely. It twists. It takes the air and spins it into a tight whirling column that reaches down from the clouds and touches the ground, and where it touches, it can tear a house to pieces. Most people picture tornadoes out on the open plains, dark funnels marching across empty fields under a green sky, easy to see coming. The tornadoes that hide inside a storm line are far sneakier. Scientists call this kind of storm a line with embedded rotation. As the huge wall of wind and rain charges forward, small pockets within it can begin to spin, twisted up by the clash of winds moving at different speeds and directions inside the line. These spin-ups form fast, drop a tornado with little warning, and lift back up minutes later, sometimes hopping along the line to do it again somewhere else. 3 things make these hidden tornadoes especially dangerous. First, they are wrapped in rain. Out on the plains, you might see a tornado from miles away. Inside a storm line, the tornado is buried in a curtain of heavy rain, invisible until it is nearly on top of you. Second, they move fast, racing along with the speeding line at highway speeds, giving people almost no time to react. Third, they often strike at night, hidden in the dark, during the same overnight hours when these storm systems love to roar to life. Add it all up and you get a tornado you cannot see, moving faster than you can flee, arriving while you sleep. Warning times can shrink to just a few minutes, sometimes less. Picture a marching band moving down a street in a straight line. Now imagine that somewhere inside that tight formation, one performer suddenly starts spinning like a top, fast and wild, hidden in the middle of the crowd where you cannot spot them until they are right in front of you. That is a tornado inside a storm line, buried in the charge, impossible to see until the last second. These embedded tornadoes are often weaker than the monster twisters of the Great Plains, but weaker is a relative word. Even a smaller tornado can lift a roof, flip a car, and turn broken lumber into flying spears, and because they strike with so little warning, in the dark, in crowded areas, they can catch far more people off guard. This is why the warning sirens and the alerts on your phone matter so much during these storms. When a line like this comes through at night, that buzzing alert may be the only warning you get. The difference between reaching a safe room and being caught in the open. The safest place is the lowest floor, in the most interior room, away from windows with something sturdy over your head. For 10 days, this pattern kept firing storms with all these weapons loaded inside them, and the reason it would not quit, the reason the danger kept coming wave after wave, traced back to a single stubborn feature stalled across the map, refusing to move. A boundary in the sky had jammed. The reason this danger dragged on for so many days came down to one thing. A boundary in the sky had stalled, and it acted like a fire hose stuck in the on position, aimed at the same region for days. Weather usually moves. A cold front sweeps through, brings its storms and rolls on, and by tomorrow the sky has cleared. That is the normal rhythm. But the giant stuck loop in the jet stream had jammed everything in place, and along the edge of the heat dome, a front ground to a halt. A front is simply the front line where two different air masses meet, like two armies pushing against each other. On one side, the hot, soupy air of the dome. On the other, cooler, drier air trying to shove in. When neither side can win, the boundary stops moving. Scientists call it a stationary front, and a stationary front is a factory for repeated storms. Here is why it will not quit. That stalled boundary is the perfect place for storms to form, lifting warm, wet air up along its length again and again. As long as the front sits still and the moist air keeps flowing in, new storms keep building in the same spots, hour after hour, day after day. It is the training pattern from before, locked in place and given a steady supply of fuel, and the fuel supply was enormous. Far to the south, over the warm Gulf and the warm Atlantic, the air was thick with moisture. Water evaporated straight off the seas. The winds around the heat dome grabbed that soggy air and carried it north in a steady stream, feeding it straight into the stalled front. Scientists sometimes call a narrow river of moisture like this an atmospheric river, and it can carry as much water through the sky as a great flowing river carries on the ground. The stalled front drank from that river without pause. Picture a garden faucet left running, pointed at one single spot in the yard. For a minute the grass just gets wet, but leave it running for hours and that one spot turns to mud, then to a puddle, then to a small pond, because the water never stops arriving and never gets a chance to drain. The stalled front did that to whole regions, only the faucet was the size of the sky, and it ran for days. No storm needed to travel in from somewhere else. The weather simply formed, poured, and reformed over the same unlucky ground. This is the piece that made these 10 days so brutal. A single storm passes and is gone. A stalled front keeps reloading, firing storm after storm at the same exhausted towns, piling rain on ground that never gets to dry, keeping rivers swollen and nerves frayed. The people below could not catch a break, because the sky itself had stopped moving on. Forecasters knew the only real relief would come when the jet stream finally relaxed and let the front move again. Until then, the hits would keep coming. But even as the land drowned, the story was shifting once more out toward the ocean, because all that warm water feeding the storms was doing something else too, something slower and far larger, gathering its strength just off the coast. The sea was about to enter the fight. Out beyond the beaches, the ocean had been quietly charging up like a giant battery, and it was about to power something bigger than any storm so far. The sea is the greatest fuel tank on the planet for storms. Here is the reason. When the sun heats the ocean, water evaporates into the air, and that water vapor carries hidden energy with it. When the vapor later rises and turns back into rain inside a storm, it releases that energy as heat, and that heat is what makes storms grow. Warm water means more evaporation, which means more fuel, which means bigger storms. And there is a magic number. Scientists have found that ocean storms need water at least about 80 degrees, and reaching down deep to really organize and grow into a tropical system. Below that, the storms stay weak and scattered. Above it, they can bloom into something powerful. By late summer, the Atlantic and the Gulf are bathwater warm across huge areas, sitting right at or above that threshold, ready to feed a storm. And the warmth has to run deep, well below the surface. A growing storm churns the sea beneath it like a giant mixer, dragging up water from below. If the warm layer is thin, the storm pulls cold water to the top and chokes on it, cooling its own fuel. If the warm layer is thick, reaching far down, the storm keeps feeding no matter how hard it stirs the water. This summer, the heat reached deep, and the ocean stood ready to give and give. This year, the water ran even hotter than usual. The same heat dome that baked the land had also been cooking the shallow coastal waters, pushing sea temperatures up along the shore. Warmer seas hold more energy, and more energy in the water means a storm can grow faster and stronger once it gets going. Forecasters watching those warm patches of ocean knew they were looking at a loaded launch pad. Picture a pot of water on a stove. Turn the burner to low and it just sits there steaming a little. Crank the burner to high and soon it boils and churns, throwing steam into the air with the real force. The warmer ocean is that burner turned up high, driving more and more moist, energized air upward, giving any storm that forms a powerful shove. All summer, waves of stormy weather roll off the coast of Africa and drift west across the Atlantic, and any one of them can find warm water and blossom. But storms can grow right at home too, in the warm water just off the coast, from the leftover spin and moisture of the very storm systems that had been battering the land. That is what began to happen here. A loose cluster of thunderstorms drifted off the coast and out over the warm water. Out there, with the ocean's fuel beneath it and the moist air all around it, the cluster started to gather itself. It grew taller, it grew wider, and slowly it began to organize into a single, connected system, the first step on the road to becoming something with a name. For that cluster to become a true tropical storm, it needed to do one more thing, the trick that separates a messy blob of thunderstorms from a focused, powerful engine of wind and rain. It needed to learn how to spin. For a messy cluster of storms to become a hurricane, it has to do one strange and beautiful thing. It has to start spinning, and the spin comes from the turning of the earth itself. Here is how it begins. Where all those storms are churning, the rising warm air leaves behind an area of low pressure near the surface, a spot where the air is thinner. Air from all around rushes in toward that low spot, trying to fill it, the way air rushes into your lungs when you breathe in. On its own, that inrushing air would just flow straight toward the center, but the Earth is spinning beneath it, and that changes everything. Because our planet turns, anything moving across its surface gets gently nudged to the side. In the northern half of the world, moving air curves to the right, so instead of flowing straight into the low center, the inrushing air gets bent, curving around it, and the whole mass begins to rotate. Slowly at first, then faster, a giant lazy spin takes hold across the storm cluster, turning like a merry-go-round. Once the spin starts, the storm begins to build itself. The rotation helps organize the scattered thunderstorms, pulling them into curved bands that wrap around a common center. That center becomes the heart of the system, and the storms feed it, and the spin tightens, and the whole thing grows stronger and more focused. A loose blob of weather becomes a single turning machine. There is a lovely comparison for what happens next. Picture a figure skater spinning on the ice with their arms stretched out wide, turning slowly. Then they pull their arms in tight against their body, and suddenly they whirl much faster without any extra push. Spinning air does the same trick. As the storm pulls its winds inward toward the center, the spin speeds up on its own, and the winds around the core climb higher and higher. Scientists watch this moment closely, because it marks a storm crossing a threshold. When the winds in that organized spin reach 39 miles per hour, the system officially becomes a tropical storm, and it earns a name from the list prepared for the season. Push the winds past 74 miles per hour, and it graduates into a hurricane, a full-grown ocean giant. The difference between the two comes down to how fast that inward spin has grown, and warm water can push a storm across the line in a single day. The cluster off the coast was doing exactly this. Satellites showed the messy blob tightening, the storms curving into bands, a center taking shape. The pressure at its heart was dropping. The winds were curving in and speeding up. Hour by hour, it looked less like a random patch of storms and more like a coiled spring beginning to turn. Forecasters faced a hard truth about a storm forming this close to shore. A hurricane that spins up far out at sea gives days of warning as it approaches. One born right off the coast, in already warm water, can strengthen and strike with far less time to prepare, all while the land below is already flooded and exhausted from 10 days of storms. The spin was tightening, the name was waiting, and the coast was directly in its path. The giant was about to be born. Off the coast, the spinning cluster crossed the line, and a new tropical storm was born, given a name from the season's list. This was the spinning giant, the ocean-born threat that had been building in the warm water while the land drowned. It was young and still growing, its winds curling tighter around a forming centre, its rain bands spiralling outward across the sea. And it sat in the worst possible place, close to a coastline already soaked and reeling from more than a week of storms. A storm like this, homegrown near the shore, is a special kind of danger. Most powerful hurricanes announce themselves days in advance. They form far out in the ocean, and forecasters track them across thousands of miles of water, giving people time to board up windows, gather supplies, and leave. A storm that spins up right next to the coast steals that time away. It can go from a loose cluster to a named storm to landfall in a short span, striking a region that has had almost no chance to catch its breath. And this storm did not arrive alone. It arrived on top of a disaster already in progress. The ground was saturated, the rivers were swollen, the drains were overwhelmed. Then this fresh system swung its heavy rain bands over the same exhausted coast, dumping even more water on land that had nowhere left to put it. Rain that a healthy landscape might have shrugged off now ran straight into the flood, pushing rivers higher, filling streets that had barely begun to drain. Picture a spinning top wound tight and set loose on a table, whirling and wandering, throwing off everything at its edges. That is a young tropical storm, a compact engine of wind and rain, spinning just offshore and flinging bands of weather onto the land as it turns. And a storm does not need to be a monster to be deadly. This one had winds far below hurricane strength, yet its true threat was the water it carried. Some of the worst disasters in history came from weak, soggy storms that crawled ashore and simply would not stop raining, dumping foot after foot of water on the same towns for days. A slow, wet tropical storm parked over an already flooded coast can do more damage than a fast, powerful hurricane that races through and moves on. The wind picked up along the coast. Palm trees bent. Signs rattled and tore loose. Waves grew tall and angry, crashing harder against the beaches with every passing hour. Boats strained at their ropes. The ocean, which had spent all summer quietly storing heat, was now hurling that energy back at the shore. But the wind was only part of the threat, and often it is the smaller part. The deadliest weapon a storm like this carries is the ocean itself. As the storm spins, its winds do more than blow. They shove the sea. They pile the water up and drive it toward the land. And when that mountain of water reaches the coast, it can flood everything for miles inland, drowning neighborhoods that sit far from any river. Coastal towns braced. Officials called for people to move away from the shore and toward higher ground, because the water was coming, and this time it would come from the sea. The storm was drawing a breath, and when it exhaled, it would push the entire ocean ahead of it. The surge was coming. The most dangerous part of a coastal storm is the water it pushes ahead of itself, a rising wall of sea called the storm surge. Here is what it is. As the storm's powerful winds blow across the ocean for hours, they do more than stir up waves. They physically push the water, piling it up and driving it toward the shore. All that shoved water has to go somewhere, and when it reaches the shallow coast, it has nowhere to go but up and inland. The sea level itself rises, sometimes by several feet, sometimes by 10 feet or more in the worst storms, and the ocean climbs right onto the land. This is different from the waves you see at the beach. A wave rolls in and pulls back. Storm surge is a steady rising flood of ocean water that comes in and stays, pushing farther and farther inland, swallowing streets, homes, and whole neighborhoods that normally sit safe and dry. And here is why it is so deadly. Water is astonishingly heavy. A single cubic yard of seawater weighs well over a ton. Now imagine a flood of it, feet deep, moving with the force of the ocean behind it. It pushes buildings off their foundations. It crushes walls. It lifts cars and boats and carries them inland like toys. Through all of history, storm surge has been the single biggest killer in hurricanes, drowning more people than the wind ever has. For all the fear that howling wind inspires, it is the silent rising water that has claimed the most lives, storm after storm, century after century. The timing with the tide matters too. If the surge arrives at high tide, when the sea is already at its peak, the flooding climbs even higher, stacking the storm's push on top of the natural rise of the ocean. Forecasters watch the tide charts closely, dreading the storms that come ashore at just the wrong moment. Picture the ocean itself standing up and walking inland, slow and heavy and unstoppable, rising up your street 1 foot at a time. There is no outrunning it once it arrives, and there is no fighting it. The only safety is to be somewhere higher and farther inland before it comes. For this storm, the surge threatened the low, flat stretches of the coast, the barrier islands, the bays, the rivers where the sea reaches in, and it landed a cruel double blow. The rain from 10 days of storms was already trying to drain out of the rivers and into the sea. Now the surge pushed the ocean the other way, up the rivers, blocking that drainage, and the fresh floodwater and the seawater met and rose together. The land was squeezed between water falling from the sky and water climbing from the ocean. This is why officials plead with people to leave the coast before a storm like this, and why they measure the danger by how high the water will climb, more than by how hard the wind will blow. A house can be rebuilt. The people inside it cannot be replaced. Yet the ocean had one more danger to give, and this one could reach out and kill on a calm, sunny day far from the storm, at a beach where the sky looked perfectly clear and safe. It waited beneath the surface, invisible. A storm far out at sea can reach a sunny beach hundreds of miles away and pull swimmers to their deaths, all under a clear blue sky. The weapon is the rip current. Rip currents are narrow rivers of water that flow away from the beach, straight out to sea, fast and strong. They form when waves push water up onto the sand, and that water needs a path to flow back out. It finds a low spot or a gap and rushes back through it in a concentrated jet, carrying anything in the water out with it, away from shore. Here is the frightening part about this storm. A rip current does not need the storm to be overhead. When a big storm churns the ocean, it sends out long, powerful waves called swells that travel far ahead of the storm itself, racing across the water for hundreds of miles. Those swells slam into distant beaches days before the storm arrives, or even at beaches the storm never reaches at all. So while the sky is blue and the storm is nowhere in sight, the surf is secretly growing dangerous and rip currents are firing up along the shore. That is what makes them such a quiet killer. Everything looks perfect. Warm sun, calm-looking water, a crowded beach. A swimmer wades in, and without warning, the water beneath them starts pulling them out to sea, faster than they can swim back. And a rip current is fast. The strongest ones move at around 8 feet per second, quicker than an Olympic swimmer can sprint. No one can outswim it by heading straight back to shore. The current is a treadmill running the wrong way, and the harder you fight it head on, the faster you burn through your strength. That is how rip currents drown people. The panic and the exhaustion do it, the wasted struggle against a current that cannot be beaten by force. The escape is simple, and it saves lives, though it feels wrong in the moment. A rip current is narrow, only a lane or two wide. So instead of swimming against it toward the beach, you swim sideways, parallel to the shore, out of the narrow channel of rushing water. Once you slip out of the lane, the pull vanishes, and you can swim back in at an angle. Float, stay calm, swim sideways, then come in. Panic is the real enemy. Picture standing on a moving walkway at an airport, the kind that carries you along whether you want it to or not. Trying to walk straight back against it wears you out fast, but step to the side, off the belt, and suddenly you are free. A rip current works the same way, and knowing this one trick can be the difference between a scary moment and a tragedy. Every summer, rip currents quietly take more lives at American beaches than sharks and lightning combined, and a distant storm like this one can supercharge them along an entire coastline at once, on beaches where people have no idea a storm even exists. The ocean was reshaping the shore now, and pulling swimmers out was only part of it. Wave after wave was tearing at the beaches themselves, dragging away the sand, undermining the dunes, and quietly redrawing the map of the coast overnight. In a single stormy night, a beach that took decades to build can lose years of sand, and the coastline itself can move. Beaches look permanent. They feel like solid ground you could stand on forever. But a beach is really just a pile of loose sand, constantly shaped by the waves, and a powerful storm can rearrange it in hours. When the big swells and the surge from this storm hammered the shore, they went to work on the sand like a giant sheet of sandpaper, scraping it up and dragging it out to sea. The numbers can be shocking. A strong coastal storm can strip many feet of beach width away in a single event, sometimes cutting the beach back by 20 or 30 feet, pulling the shoreline inland and leaving a steep drop where gentle sand used to slope into the water. The real defence for the coast is the dunes. Sand dunes are the tall mounds of sand behind the beach, often held together by grass. They are the coast's natural seawall, a barrier standing between the ocean and everything behind it. The roads and the houses and the towns. When a storm surge rolls in, the dunes take the hit first, soaking up the water's energy and blocking its path inland. A healthy dune can be the only thing standing between a neighbourhood and the sea, but dunes can only take so much. When the waves and surge are strong enough, they chew straight through the dunes, cutting gaps and flattening them, and once the dunes are gone, the ocean has a clear path to everything behind them. The next storm, or even the next high tide, can pour right through the gap. Picture building a wall of sandbags to hold back a flood. It works for a while, but the water keeps pushing, keeps pulling bags loose one at a time, and eventually it breaks through, and everything the wall was protecting is exposed. A storm does that to the dunes in a matter of hours, tearing down a barrier that may have stood for years. The damage does not stop when the storm leaves. Homes built close to the shore suddenly find the beach that protected them has vanished. The sand swept away, the waves now reaching their foundations. Sometimes the ground beneath a beach house erodes away entirely, and the house is left standing on stilts over open water or collapses into the sea. Whole stretches of coast are redrawn, the map from last week no longer matching the land today. This is the slow, grinding cost of a storm like this, the part that shows up after the wind dies down. The coast is a living edge, always shifting, and a single fierce storm can push it back in one night, by an amount it might have taken nature many quiet years to build. 10 days. That was the length of this ordeal, from the first buckle in the jet stream to the storm clawing at the coast. And that length, that relentless piling of hazard upon hazard, was the true horror of it. To understand why, you have to step back and see the whole chain at once, and ask a hard question. Why is a slow siege so much worse than a single hard blow? A single, terrible storm is a punch. 10 days of stacked hazards is a beating, and a beating breaks things a single punch never could. Think about what this pattern actually did, one blow after another. First the heat dome, baking the land and straining the power grid, then the storms exploding along its edge, the derecho with its wall of wind, the straight line blasts and hidden tornadoes, the training storms and the flash floods, the drowned basements, the stalled front feeding it all, and finally the ocean rising up, the tropical storm, the surge, the ravaged coast. Each of these alone would make the news. They came stacked on top of one another, in the same region, in less than 2 weeks. The danger of a long siege like this is that nothing gets a chance to recover, and every hazard makes the next one worse. Start with the ground. The first storm soaked the soil and filled the rivers, so when the next storms came, the water had nowhere to soak in, and the flooding was worse than it should have been. Then the surge blocked the rivers from draining, so the water rose higher still. Each water event landed on a landscape already drowning from the last one. The hazards were joined together, they fed each other. The same stacking hit the people trying to help. Emergency crews can handle one disaster. They rush in, they rescue, they repair, they rest, and they are ready for the next one. A 10-day siege gives them no rest. The same exhausted crews who pulled people from flooded cars on day 3 were still working on day 9, running low on sleep, supplies and equipment. Every downed power line they fixed, the next storm knocked down again. Every road they cleared flooded once more. Their strength wore down just as the demands piled up, and it wore down the people living through it. Losing power for one hot night is miserable but survivable. Losing it again and again over 10 days in dangerous heat, then facing floods, then a storm, grinds people down. The elderly man who made it through the first heatwave is weaker for the second. The family whose basement flooded once has nowhere dry to go when it floods again. Danger that would be manageable in a single dose becomes deadly when it never lets up. Picture a boxer in the ring. He can take one hard punch and shake it off. But round after round of body blows with no time to catch his breath between them is what finally drops him. The endless accumulation ends the fight. The wearing down, the damage that stacks faster than the body can repair it. That is what a stuck weather pattern does to a region. It removes the one thing people need most between disasters, which is time. Time to dry out, to rebuild, to rest, to prepare. Strip that away, and even ordinary hazards turn into a catastrophe. And yet, through all of it, there was one force working in humanity's favour the entire time, quietly saving lives from the very first day. Long before the heat arrived, before the first storm fired, people already knew this was coming. The question is, how? How can anyone see 10 days of chaos before it begins? The reason people could brace for this chaos before it began comes down to one of the greatest achievements in all of science. We can now see the future of the sky, days in advance. It starts with watching. Every hour of every day the planet is measured. Satellites stare down from far above, tracking clouds, heat, and moisture. Weather balloons rise from hundreds of stations, sniffing the air all the way up. Buoys bob in the oceans, radar sweeps the skies, and airplanes report conditions as they fly. Together they gather millions of measurements of the atmosphere, a snapshot of the entire sky at one moment in time. Then comes the hard part, turning that snapshot into a forecast. The air obeys the laws of physics, it follows rules, the same rules whether it is a breeze or a hurricane. Scientists have written those rules as math, and they feed the snapshot of today's sky into gigantic supercomputers that solve that math over and over, stepping the atmosphere forward minute by minute into tomorrow, and the day after, and the day after that. These machines perform quadrillions of calculations to trace where every parcel of air will move. That is how a model saw the jet stream about to buckle days before it happened. But the sky is tricky, and forecasters have a clever way to handle its surprises. Instead of running their forecast just once, they run it many times, each time with tiny changes to the starting conditions, because no measurement is ever perfect. If all those runs agree, forecasters know the future is fairly certain. If they scatter in different directions, they know it is a toss-up. This lets them speak in odds, telling you what may happen, and also how confident they are, which is why a forecaster can say the chance of storms is high or low rather than simply guessing. Picture a great chess player studying the board. She sees several moves ahead, tracing how the pieces will likely shift, spotting the danger long before it arrives. A weather model does the same with the sky, reading the position of the pieces today and playing the game forward, seeing the trap the atmosphere is setting days before it springs. There is a limit, of course. The farther ahead you look, the blurrier it gets. Tiny errors grow with time, so a forecast for tomorrow is sharp, while a forecast for 10 days out is more of a warning of what may come. That is why forecasters watched this pattern for days as it sharpened into focus, updating their warnings as the picture grew clearer, giving people more and more specific guidance as the danger closed in. Every warning issued, every alert that buzzed on a phone, every plea to find cool air or move to higher ground, traced back to this quiet triumph of science. It could not stop the storms. What it did was priceless. It gave people time, the one thing the stuck pattern was trying to take away. Still, seeing this coming raised a bigger, heavier question, one that reaches far past any single 10-day stretch of weather. Patterns like this seem to be growing more common and more intense, and the reason may be tied to something happening to the whole planet. Scientists are watching patterns like this one grow more intense, and much of the reason traces back to a warming planet. Some of the links are rock solid, others are still being worked out. Start with what is certain. Warm air holds more water than cool air. This is basic, settled physics, measured in labs long ago. For every degree the air warms, it can hold several % more moisture. So as the planet heats up, The atmosphere carries more water vapour, and when a storm wrings that water out, it falls as heavier rain. The same storm in a warmer world simply drops more water, which means worse flash floods from the same setup. Picture a sponge that grows a little bigger every year. Squeeze it, and more water pours out than before, even with the same squeeze. The warming atmosphere is that growing sponge, and the extra water it holds comes down in the downpours that drive floods. The oceans tell a similar story. As the planet warms, the seas warm too, storing more heat in that giant fuel tank. Warmer water gives storms more energy, which can help them grow stronger and intensify faster, and higher seas let storm surge reach farther inland. These connections are well supported by the science, measured in storm after storm around the world. Then there is the heat itself, the simplest link of all. A hotter planet means heat waves that climb higher, last longer, and strike more often. Records that once fell rarely now topple summer after summer, and the deadly heat domes that start patterns like this one are landing harder than they used to. Now for the part scientists are still debating. Some researchers believe that as the far north warms faster than the rest of the planet, the jet stream is weakening and growing wavier, which could make those stuck, blocked patterns more common, the very kind that trapped this heat dome and stalled this front for 10 days. It is a reasonable idea, backed by some evidence, and it worries many experts. But it remains an active area of research, with scientists still testing whether the pattern truly holds. Honesty means saying clearly which parts are proven, and which parts are still open questions. Beyond debate is the direction things are heading. Heavier rain, hotter heat, stronger coastal storms and higher surge are all becoming more likely as the world warms. Even if the exact behaviour of the jet stream stays uncertain, the ingredients that made these 10 days so dangerous are being loaded more heavily with each passing decade. This is why events like this matter far beyond the region they strike. They are a preview. They show us what a warming world can throw at us when the atmosphere lines up the wrong way, and they push us to build stronger, warn faster, and prepare better for the storms still to come. Understanding the sky is the first step to surviving what it does. For now, though, the people of the coast needed only one thing. The thing they had been praying for since the first hot, breathless night 10 days earlier. They needed the sky to move again. They needed the giant loop to let go. And at last, 7 miles up, the wind was beginning to shift. At last, 7 miles above the exhausted coast, the giant loop in the jet stream began to let go. For 10 days it had held its shape, a towering ridge locked over the east, a deep trough carved to the west, the whole pattern frozen in place. Now, slowly, the wave started to flatten. The ridge relaxed. The trough filled in. The high, fast river of wind, which had buckled into that enormous curve, began to straighten and smooth out, the way a whipped rope finally settles once you stop shaking it. And as the wind straightened, everything it had trapped was set free to move. The stalled front, pinned in place for so long, finally lurched forward and swept out to sea, taking its endless storms with it. The heat dome, its grip broken, collapsed and drifted apart, and for the first time in over a week, a genuinely cool breeze slipped across the land. The tropical storm, steered by the shifting winds, curved away from the coast and out over open water, where it would spin itself out far from shore. The sky, for 10 days a machine of hazard, went quiet. The morning after felt almost unreal. The sun rose on a coast that had been through everything the atmosphere could throw at it, and it rose gently into clear, calm, cooler air. Birds again. A soft wind. The kind of ordinary forgettable morning that 10 days earlier no one had thought twice about. Only now it felt like a gift. But the calm returned to a changed world. The water slowly drained from the streets and basements, leaving mud and ruin behind. Crews worked to clear the fallen trees, restring the power lines, and reopen the roads. Families returned to soaked homes to see what could be saved. Along the coast, the beaches were narrower, the dunes cut through, the shoreline redrawn. The land carried the scars of 10 days that would take months, sometimes years, to heal. And the people carried something too, a hard lesson in how fast the ordinary sky can turn dangerous, and how much a little warning and a little preparation can matter when it does. Step back and look at the whole chain one more time. A single bend, in a single wind, 7 miles over our heads, reached all the way down and shaped 10 days in the lives of 100 million people. It baked cities, drowned basements, flattened forests, and stirred the ocean into a storm. All of it flowed from one loop in the jet stream, a feature most people will never see and rarely even think about. That is the quiet, staggering truth this event leaves behind. The sky above you is a vast and restless machine, always in motion, holding powers that can turn a summer week into a fight for survival, and it answers to rivers of wind you cannot feel and cannot see. The good news is that we are learning to read it. Every storm like this teaches us more, sharpens our warnings, and buys the people in its path a little more time. And time, as these 10 days proved, is everything. So the next time you step outside into an ordinary quiet sky, look up and remember. Far above the clouds, the wind is always writing the next story. The only question is when it will decide to tell it.